Doctor, I need your
Yes, I
approval to
will.
share screen.
Yes, you can share.
Thank you.
Okay, so first, it's a very interesting topic. Now, concerning, can you go to slide 22, please? Okay, Sharif, can you just
It didn't appear.
no, yes, it appears. It appears. Can you give a small explanation of this graph?
Yes, Akid. So it depends with time. So we can see the variation in the hash rate. Okay, the colors here, the darker colors are uh, energy sources that are not environmental friendly, and the lighter ones are renewable energies. And you can just see that the hash rate. So miners have relied more on renewable energy. It depends on the season actually. So as the months change, it seems like miners are switching, are relying more on renewable, not renewable energy, I mean polluting energies. So it's just an overview, and depending on the areas coming of the activities based on the regions where miners are based.
Okay.
So just
Can
to show that renewable energies cannot cannot supply the required amount of energy constantly.
okay. And please go to slide 24.
Yes.
Here in the economical analysis and assessing the net present value, do you know what were the assumption taken? What was the confidence in
Yeah.
future number?
Yeah, I can answer this. So in terms of
Yeah, just
assumptions,
Karim, just 1 minute, please.
oh, sorry.
Sharif, do you have an idea?
You want? Yes. So they assumed that okay, the basic assumptions here are that uh, in the beginning of each month, we assess whether we want to stick to selling electricity to the spot market, or we're gonna rely mainly on selling on mining with the energy. So we can't, in the middle of a month, decide to change the use of the farm. And so they also considered that it would cost around $2 or $3 million to set up the mining farm, which is also something that should be taken into consideration. But for the probabilities and the numbers, more than that, I don't have the numbers right now. But
Okay,
the main
just can you tell me what
assumption.
is okay, no problem. Can you tell me the difference between the main three cases and the three cases you are studying?
Yes. Yes, okay. So the main one was the normal one, selling to the spot market. The second case here, it's more interesting. So the second case is they just saw whether لا مش whether, so they used the farms during 2 years, the mining farms and the wind farms during 2 years with the same equipment to see how much they could make a profit. And in the third case, what they did is just that they renewed the mining equipment, because mining equipment has a lifetime of around 2 years or 2.5 years. So it's just to show that the fact of renewing the equipment, reinvesting in new equipment, will provide a better return. So in terms of it's just the mining equipment that was renewed, and 4 years of activities rather than 2. And many cases could be taken into consideration because of the situation where so in these countries, they get the approval for such projects 6 years in advance, and it takes only 2 years to build the farms. So the wind farms. So they have 4 years either to waste and not do nothing, or they can start trying to pay back their project.
Okay, thank you, Sharif. Karim,
Thank
can
you.
you give us little details about the assumption and the confidence in future?
So in terms of confidence in the future, what do you mean exactly?
So in general, when we determine the net present, we will take this together during this course, but when you calculate the net present value, you should also take into account the risks that you are having in your project. If you are not considering risks, then you mean that for you, the value of money will remain the same. This is what we mean, okay? So for example, if you have $100 today, let's say you can buy a thing, you can buy it also after 1 year. So in case you don't have a high confidence in the future, the value of your money will be decreased. So what you buy now with $100, you will buy it after with $200, let's say. So we have a factor called confidence in future that will be used in the calculation of net present value. Here, if you just compare the cost, the initial cost to the benefits you have, then without taking any risk into consideration, then this will be a study without with 100% confidence in future. So you don't have your value of your money will be the same with time. This is what I mean.
Okay, I see. So in terms of what you're talking about, I think that they've included this through the probability of negative NPV. And this is what I'm guessing. No, we haven't seen this specifically mentioned. And in terms of the assumptions, it's mostly what Sharif has mentioned, but I'll repeat them, no problem. So the first assumption is that we're building a mining farm, and this mining farm obviously has an initial investment, which is around $3 million. So we are assuming that the owners of the wind farm have this capital at hand. The second assumption being that at the beginning of each month, the decision is made on whether the wind farm is selling the energy to the spot market or whether it is using this energy to produce or to mine Bitcoin. And finally, the third assumption is that the price of electricity or the price of the cryptocurrency was assumed to be constant throughout the whole month. Obviously, both of these markets have a lot of volatility in them, so it means that this assumption is important in this case.
Okay, thank you. Just now for slide 27, please. Can you go to slide 27? Concerning this analysis, Karim, you did it yourself?
So the second part was done. It's very easy. You can do it on the site, which is CryptoCompare. So you basically put your power cost on the right, and it will basically, and you put obviously the type of hardware that you are using, and it calculates how much Bitcoin you are expected to mine per day, and it gives you the profit per day, since it has embedded.
Okay, but I mean, أنتوا عملتوها هيدي, يعني you introduced the value, or already it was in a certain research or in an article?
The part before this, I think it was used in a problem or something. But we calculated this with the initial with the conditions that we used, and the part of cryptocurrency is.
Yani your calculation started from which slide? From here?
This one.
From this.
Yes.
One. Okay.
Yes,
okay,
we entered the values on the specific day. Yani this is not from research. This is from our. We took the initiative to.
Okay.
This is a screenshot of our finding.
Thank you. Okay. Thank you so much.
Thank you.
Thanks. Thanks a lot.
Okay, so we still have Marwa today, I think. Marwa, are you ready?
Yes, doctor, I'm ready.
Yeah. You can share your screen.
All right. Can you see my screen?
Yes, I can see it.
Okay, so hello everyone. My project talks about compressed air energy storage and discussing the system itself and how it works, different types, and assessing it, talking about health and safety and the concerns and recommendations. So compressed air energy storage systems, or CASE systems, are not entirely new energy storage units. They actually date back as far as the 1970s. The system's flexibility allows for additional equipment to be added to the backbone setup itself, or even its coupling with other systems to enhance their performance, and we'll discuss this later. So the main aim of CASE plants is providing sufficiently large energy storage by compressing air into a specific storage unit and later discharging it when needed, and subsequently producing and supplying electricity. So the first CASE plant was built in Huntorf, Germany in 1978 due to a high demand for large-scale energy storage units. The land's geological location promoted its construction as 2 underground salt caverns were present and would readily serve as air storage units. So the second plant was built in 1991 and is located in McIntosh, Alabama in the USA, and both plants continue to be fully operational more than 30 years later. These advancements in CASE systems and the research around them, coupled with the recent worldwide shift in energy sector to clean and renewable energy, make them very attractive energy storage systems. Another important feature is their ability to continuously store energy and therefore consistently generate electricity, as opposed to other renewable energy sources which are intermittent with a fragmented supply like wind or solar energy. So a detailed description of the CASE system will help in grasping its importance as an eco-conscious, large-scale energy storage system. The operating system is quite basic, applying the simple engineering concept of compression, expansion, and transformation of energy from one form to another. In this charging phase, we have the air coming in from the surroundings, which is considered a low-pressure reservoir. It is compressed by an electrical power source into a tank or an underground cavern to store it. And this changes the electrical energy into kinetic and then potential energy. During the discharge phase, air is expanded and heated and is driven into a gas turbine, which then supplies energy to a generator or a power grid, thus generating electricity. This changes mechanical energy, specifically kinetic energy of the turbine's rotors, into electrical energy. So the main components of the system are the compressor, turbine, and the air storage space. Compressors used in the CASE system are usually radial compressors, which push the air from the center in the direction of the radius and is driven by centrifugal force, or they can be axial compressors, which push the air backwards along the direction of the axis, which compresses the air. In both types, of course, the air leaves at a higher pressure and heat is generated from this compression. Turbines, as we said, they generate electricity by changing kinetic energy of the rotating shaft into electrical energy through its connection to a power grid or a generator. To rotate the shaft, air is introduced into the turbine at very high temperatures after having entered a combustion chamber and is expanded to reduce its pressure. Recuperators, which are special types of heat exchangers, can trap and recover exhaust heat generated from the turbine and is shown to have an improved efficiency by up to 10%. And we'll talk about them later and how they can be implemented into the system. The air that's compressed, of course, needs to be stored in a certain space or unit, and this depends on the desired operation, whether small scale or large scale, the geological formations, and the material availability. So there are two types of air storage systems, and they are isochoric and isobaric storage systems, and they can each be above or below the ground. In isochoric storage, the volume of the air is kept the same and the pressure is allowed to vary, such as in tanks, salt caverns, or even aquifers. This type of storage is most common, but the drawback is the decreased efficiency of the process due to the fluctuating pressure, which might cause difficulties for the equipment's design operation, the operating conditions. But it is very widely used. The large-scale CASE operations require a large volume to store the compressed air, which are usually underground. This allows the system the ability to store a large amount of energy and benefit from smaller space consumption above the ground. Underground salt caverns are usually used. For instance, the Huntorf plant in Germany has not one but 2 underground salt caverns in use to store the compressed air. But it is important to note that the process of preparing the cave for use is a very long and diligent one. Now, the other type of compressed air storage that is not very widely used, but it is studied, is isobaric air storage, where the pressure is kept at a constant value, but the volume is allowed to vary. This can be achieved by connecting the storage volume to another liquid reservoir to offset any changes and maintain a constant pressure head, or by placing the volume usually in a balloon-like structure below the water, where the overhead pressure of the water compensates for like the different volumes that we might need. Here we can see the Hunter plants, the salt cavern and the depth and their sizes relative to other parts of the system above the ground, which is actually quite huge. So there are three types of case systems: adiabatic, diabatic, and isothermal. In adiabatic case systems, upon the compression of air, heat is generated, of course, and this heat is captured and stored so it can heat the air during discharge phase before it enters the turbine. In principle, this relieves the system of any need for any fossil fuels for the combustion chamber, and which makes the process extremely environmentally friendly. The storage of heat occurs in thermal energy storage units, where the most efficient is heat exchangers, although some systems can use crushed rocks or certain types of solids and fluids. In diabatic systems, heat generated is allowed to dissipate into the surroundings and there's no capture of it. Instead, there are intercoolers which lower the temperature of the air that is compressed before it enters the cavern. The first two operational systems in Germany and USA are both of the specific type. However, in this setup, additional heating of the air is required upon its discharge into the turbines, of course. And finally, the isothermal case systems, heat is allowed to be exchanged with the surroundings, so in and out of the system, in order to maintain a constant operating temperature. Intercoolers are needed in this method to cool the compressed air before it enters into the cavern in order to ensure it is at the same temperature of the inflow of air. This means that if there were no intercoolers present, then a relatively slow air intake must be maintained to give the system enough time to actually expel enough heat to the environment in order to uphold a constant temperature in the system. In order to maintain thermal equilibrium, of course, the same amount of heat lost when compressing should be supplied upon expansion as well. Concerning the efficiency of the systems, diabatic systems can go up to 42%, such as in the Hunter plant in Germany, but literature shows that adiabatic and isothermal systems where the value is actually can go up to 70% theoretically, which is quite high. In this table, we can see the difference between the three types of case systems. We can see the efficiencies and the power range. For example, we can see the isothermal systems have the greatest operational ranges. Now, the Hunter plant in Germany was the first case system to be built in 1978, as we mentioned previously. It operates diabatically and produces an output power of 290 megawatts. In this system, we have two compressors in series at a low pressure one followed by a high pressure one without any type of thermal energy storage device to capture the heat because it's diabatic. Two underground salt caverns with a total volume of 310,000 meters cubed are available for air storage and are kept at a pressure ranging from 46 to 76 bars. For the discharging, where the air is depressurized to 42 bars and is heated before entering the high pressure gas turbine, where the outlet pressure of the air is now 10 bars. And then again, it is further heat entering the low pressure gas turbine. And we do this because the operational and design constraints make it necessary for the increase of the air temperature and decreasing its pressure and maintaining it at a constant value before entering both turbines, of course. Now, the McIntosh plant in USA was built in 1991, and it operates diabatically as well, but produces an output power of 110 megawatts and has only one underground cavern for air storage, but its total volume is 538,000 meters cubed. No thermal energy storage systems are integrated here, although the main difference is the installation of recuperators that actually use the heat from the first expander and use it to heat the air flowing into the second turbine, and this helped in making the system more efficient. Now, in any undertaking project, of course, we need to consider the design, but we also need to consider its financial viability. So The expenses of CASE include capital costs, of course, which encompass construction of the plant with the operation units and operational and maintenance costs, as well as replacement and safe waste disposal costs, which is also very important. Of course, there is the cost of preparation of the cavern if it is needed. To get an idea about these costs, we can look at a study done that compares energy storage systems and is projected to expected prices to 2025. We will compare CASE systems to pumped hydropower storage systems since it's considered a market competitor as both store energy in bulk and are able to discharge electricity for hours at a time. So very briefly, based on the data, the total project cost of CASE falls in the middle with $1,669 per kilowatt as opposed to $2,400 per kilowatt for pumped hydro storage. And we can also see for ultra capacitors, it's $930 per kilowatt. This can give us an idea about certain costs to investors, but of course, each system would differ depending on the type of CASE system and the equipment that is used. Now, another study was done to compare the factors on different fronts, such as environmental, economic, and technological fronts, while considering storage systems. And these three were proved to be the most important factors, according to experts. So the CASE systems ranked second after thermal energy storage systems, but pumped hydro storage systems ranked fourth in the study, although it has the highest installed capacity of energy stored globally. So it is used a lot, but the system is not environmentally sustainable, which is the most important criterion according to experts. And CASE systems have shown to be financially feasible relative to other alternative energy storage systems with comparable capacity. Although it might seem costly at first, but CASE is relatively feasible for being such a huge storage system because it can store in bulk. But since it ranked second, it is important to actually disclose the disadvantages of CASE systems in order to leave no room for ambiguity. So one of the biggest disadvantages right now is the heating of the air before it enters the turbine, and the additional heating is now done by burning of fossil fuels, which is obviously harmful for the environment. However, this can be offset by the newer CASE systems, which regenerate the heat that is lost, or by adding recuperators like an isothermal. Another disadvantage is on the safety side. Since we cannot completely eliminate the hydrocarbons that might be present in the underground caverns, then this poses an everlasting safety hazard. But of course, we can't forget that any system is bound to pose potential safety hazards. However, with the implementation of safety measures and the procedures, accidents can be minimized and will be discussed in a bit. So again, of course, the system needs to be the operational system needs to be safe and environmentally friendly. So we'll now look at the threats concerning these two factors. The biggest negative impact on the environment due to CASE systems is currently the burning of fossil fuels in the combustion chamber. So this is, of course, very unsustainable and harms the environment since it leads to direct emissions of greenhouse gases, mainly CO2, which trap heat inside the Earth's atmosphere and consequently contributes to global warming. But with newer CASE systems, again, this is avoided since the energy is harnessed again by different methods. Another very important consideration is the safety compromises that might be present, and this might mainly due to fire hazards, which are prominent since hydrocarbons are usually present in underground caverns. To understand how fires start, we can consider the fire triangle, shown over here, which says that we have three components to start a fire, which are oxygen, fuel, and heat. And these contribute to a fire actually igniting. And with an fuel-to-air ratio, which we'll discuss as well. Oxygen would come from the air, which is compressed into the cavern. The fuel would come from the hydrocarbons that might be lingering in the storage space. And the heat would come from the ignition sources that also we'll discuss later. However, this is also, we should keep in mind that there's the fuel-to-air ratio, which actually represents the amount of fuel inside the air, or the hydrocarbons basically inside the air. It should also, of course remain within a certain limit called the flammability limit, and upon exceeding this limit, then a fire surely ignites. So these are the ignition sources, or some of them, the main ones. Some are natural, some are induced. It is important to, of course, eliminate the sources or try to minimize their effects to ensure that there is no fire hazard. First off, we have adiabatic compression, which produces heat, and the high pressure existing already in the caverns both contribute to being an ignition source. We have piezoelectricity that should be taken into account. This phenomenon takes place in the crystals that might be present in the earth inside the cavern, where charges are redistributed and can accumulate on different sides of the crystal upon applying any stress. So we also have lightning, which can reach, of course, very high temperatures and has been known to be a direct ignition source, especially when it hits equipment on the surface. And finally, we have friction, which can contribute when the changes in pressure upon air entering or leaving the cavern. It might induce friction on the surrounding rock formations. So these dangers, the dangers of these hazards can be reduced where many safety procedures can be taken in order to ensure that the plant system operates more safely. So low pressure air purging is usually implemented where the air is diluted and the fuel to air ratio can be controlled and kept within the flammability limit. Pressure gauges can be installed to continuously monitor this pressure. Another measure that should be taken into account is completely sealing off the storage facility to prevent any escaping gases that might that of course might act as an ignition source. Automatic shut-off valves need to be placed in an airtight space to be able to relieve any excess pressure that might be built up in the system. Because of the compressed gas, of course. The gas that is entering the turbine should also be monitored in case there is any leak where their composition might be changed if hydrocarbons are present in the cavern. So case systems have progressed widely throughout the years. However, there is also always room for improvement. Most of the energy lost is at the level of the turbine and the compressor, as well as any type of heat exchangers that are usually present in newer systems. This is important when studying the efficiency of the system since it lowers it the more heat we lose and don't collect back. Another thing to keep in mind is the air storage facility systems that can also contribute to the overall power output. So depending on how much we can actually store, this is related to how much we can actually produce, like the electricity we can produce. And of course, it affects the efficiency. And as for the future, further studies are needed to find the optimal and most efficient configuration of compressors, turbines, heat exchangers, storage systems. The system's sustainability is also a crucial point to consider upon further enhancing these systems. It is important to ensure that there is no harm caused to the environment, especially upon preparation of the underground cavern, which should not cause any damage whatsoever to the geographic site, especially if there are any valuable aquifers present upon digging. Another important sustainability factor is the minimalization of energy consumption, which can be achieved by coupling the system with another, which might not be continuous operating system like solar, wind energy, which are intermittent fluctuating, and the system can actually act as a co-generating system. An interesting study actually shows a case system with a CO2 capture unit to capture any greenhouse gases that are emitted from the combustion chamber of the turbine. And the captured gas can actually be used for multiple production purposes, such as fertilizers or building materials. So in conclusion, case systems have proved to be fully operational with relatively high efficiency and startup flexibility. The system can operate isothermally, diabatically, or adiabatically. The storage units can be isochoric, like in tanks or underground caverns with a constant volume, or they can be isobaric and stored in an underwater facility with constant pressure. This all renders the system very accommodating and flexible as compared to other storage systems. Although diabatic case systems are the only ones that are implemented commercially now, isothermal and adiabatic systems, which have up to 20% higher efficiency, are expected to soon be operational. Due to the growing decarbonization movements and the shifting towards renewables, the system's importance is obviously amplified, seeing as it can serve as a direct energy storage system, which readily discharges electricity, or it can be complementary to intermittent renewable energy processes. Large-scale, eco-friendly, continuous energy storage systems such as CAES are sure to be a point of interest with the increase of energy demand for all small-scale and industrial processes. And actually, there are several projects which have started development in the US and the UK, which would operate adiabatically and isothermally, both of which are much more eco-friendly, obviously. And these are my references. Thank you.
Thank you, Marwa. First, for the report is very good, and also thank you for the presentation. Can you go please to slide 11?
Yes, of course. 1 second. Yes.
Okay, can you please explain in brief the cycle here, Marwa?
Yes, of course. So first we have air coming in, and we have a motor to usually to pump the air in. It comes in at a low pressure, and then it enters the compressor. It is compressed, and then it is cooled down, and then just for a bit, and then it goes again into a high pressure compressor, and then it enters the cavern, and then upon its discharge, it enters first a high pressure because it is stored, of course, at a high pressure. It enters a high pressure turbine, and then it is further heated after it goes out, and then it goes out to another low pressure turbine because now the pressure is decreased. It goes into a low pressure turbine, and it exits into a generator, and we have the recuperator, which takes the heat from the turbine, the excess heat, and it uses it to heat the air that is discharged from the cavern.
Okay. Marwa, here you studied compressed air storage. Did you try to compare with water storage? Because, you know, in general, the heat capacity of water is larger than air. So can you tell me about the comparison between the two?
Yes, so there's pumped hydro storage, which actually the way it works is they take the water, a large amount of water, of course, and they place it in a storage unit or a storage facility, usually in the ground, like above, but deep in the ground. And then it's stored at a very high level, so it has a lot of potential energy. And then this water, when we need electricity, they allow it to flow down, and once it's flowing down, the water passes through a turbine, and this turbine generates electricity. But this is not environmentally friendly, as I said before. Since it can cause flooding, it causes the system itself causes a lot of emissions.
Okay, can you go please to slide 13?
Yes.
Can you please give the main conclusion you can take from this graph?
Yes, so from this graph, I focused mainly on, of course, CAES systems and the pumped hydro storage because I talked about it before, and the first place, which was thermal energy storage systems. So here, the experts were actually comparing the performance index and degree of utility, so how feasible it is to work with this system. We see that CAES ranked second. Just because of the disadvantages I talked about, but this is because they operate diabatically right now. And the pumped and thermal hydro storage units, of course, like they ranked first, especially because of the environmental factor, because they are very environmentally friendly, which proved to be the most important index, which we compared against. And then the pumped hydro storage actually ranked fourth, which shows that even though it is very widely used, it is not the environmental impact actually lowered its rank in comparison to the other storage units, storage systems.
Okay, Marwa, thank you so much.
Thank you.
So guys, hopefully we continue to gather the presentations next time, okay? See you next time. Bye bye. And concerning this week, I will tell you which videos to go over. Okay?
Okay, thank you.